Today I'm going to start talking about the scientific measurement and calculations notes. If you have my packet printed up, I would follow along with that because it will help to write things down. So we'll start off talking about the SI units, and we'll get into the metric prefixes and what each prefix represents, and then we're going to get into significant digits or significant figures, what they mean, how to count them, and all that kind of stuff. So let's get started. Now, a lot of times people say international system, although the abbreviation is SI system, and it's because the scientists that made this up met in France, so they got the French pronunciation shown here. I'm not too worried about that, but sometimes I have people ask that. Alright, so the SI unit, the prefixes, not the prefixes, the base units for the international system. There's a couple of them shown on the screen here, and we are not going to worry about the last two rows here. I just put them up there because they're in the textbook and you'll see them online if you look them up and everything. And we don't really have to worry about those. If you copy them down, that's fine, but if you don't, it's not a big deal. They're not going to come up. But things like length, it gets the symbol of a cursive L. I am not going to ask you to remember that. It's in the system, so I put it up there, not a big deal. But the base unit is a meter, right? We're not talking feet and inches, science class, so we're going metric, it's meter. The abbreviation for meter is a lowercase m. Mass is also a lowercase m. Sometimes people look at this and think they're going to get confused with these things because they're both lowercase m. They're not really going to come up in a way that's going to be confusing for you like that. Now, mass is an interesting one because the base unit is a kilogram. It's the only one that has a metric prefix here of kilo. All right, and that's kg. Time is measured in seconds. Temperature is not Celsius, it's Kelvin. We'll talk about the difference between Celsius and Kelvin another day. It's pretty easy to convert between those two, but notice it's not Fahrenheit. Amount of substance, and this is something that we are going to end up spending a lot of time on this year in chemistry, is a mole. Right? We're not talking about that little fairy creature that lives underground. Moles, if you remember physical science, it was probably brought up there. Now, scientists love to abbreviate things, and you're going to see that throughout this year. Right? So mole, they abbreviate it MOL, so they leave off that E. Right, so you're going to see abbreviations all the time in this class, and I'll point out what they are, and I don't think you'll really have a hard time remembering what they are, but these are the International System of Units. Now, the prefixes for the metric system, we're going to go through this, and a lot of this you've heard already, I think. The base units are meters, liters, grams, things like that. And I have this scientific notation off to the side, and we'll talk about scientific notation in detail another day too, but whenever you have something raised to the 0 power, that's basically like saying 1. All right, deca is an interesting one. It's the only one that has two different symbols that people can use, DA or DK. And to be honest, deca is probably not going to come up much in our class. It doesn't get used that much, but say you have a decagram. It's 10 times bigger than a gram. Hecto is 100 times bigger. Now you're getting in the scientific notation of 1 times 10 to the 2nd power. Kilo is 1,000, that's 1 times 10 to the 3rd. Mega, now this one gets a capital M as a symbol. All right, you want to pay attention to that. That's a million times bigger, which is 1 times 10 to the 6th. Giga, capital G. All right, you're getting into 1 times 10 to the 9th. These are all larger than 1. Now we're going to go the other way. Deci. Notice deci is a lowercase d, which is why deca has an extra letter in there, because I didn't want deci and deca to get confused. Deci will probably get, well, deci doesn't get used that much either. It's 0.1, it's a tenth, so it's 10 times smaller than the base unit, and that's 1 times 10 to the negative 1. Notice the scientific notation, the exponent now has a negative value. Centi is 0.01, so it's 1 times 10 to the negative 2. That's 100 times smaller. Milli, now this one's lowercase m. Remember I pointed out mega's capital M, milli's lowercase m. Milli will actually get used a lot. Right, so a milligram, for example. So that's 1,000 times smaller. You have micro, which if you drew this, if you wrote this as a lowercase u, I would be fine with that. It gets that symbol there, mu. All right, you're talking about 1 times 10 to the minus 6 Nano is getting even smaller. That's 1 times 10 to the minus 12th. And then you have pico. I'm sorry, nano. I gave the wrong exponent there for nano. Nano is 1 times 10 to the minus 9th. Pico is 1 times 10 to the negative 12th. Now for us, most of the metric system that we're going to use is going to be between kilo and milli. Majority of them will be that. Every once in a while you might get giga or mega or micro, nano, or pico, but majority of the time it's kilo to milli. There are things that are bigger and smaller. There's tera, like if you think about memory for a computer, so it's terabytes. And there's things that are smaller than micro, nano, and pico. There's alto, femto, there's all sorts of stuff, but these are the ones that we're really going to focus on. Now, the meaning of these things, all right, that base unit, that's just 1. Deca is 10, so it's 10 times bigger. Hecto is 100, 1,000, million, and billion. Now, as you go smaller, you get tenth. And notice the difference here, and this is stuff that I'm sure you learned in math class before. We just wanted to re-emphasize this. Once you start getting smaller than 1, you have to add this th at the end. Tenth, hundredth, thousandth, millionth, billionth, and trillionth. All right, pay attention to that. Now, if you're copying this stuff down, feel free to pause the video while you write it down. You know, something like that's perfectly fine. Now, the reason why we wanted to get into that is we're going to start counting significant digits, and it's one of the first things that every chemistry class is going to talk about. So really what happens is there's 2 different types of values when we are talking about numbers in chemistry. There's things called exact numbers, and they're the easier ones to deal with. There's no measuring that had to occur for exact numbers. You can just count objects. So like the example up on the screen, 24 desks in a room, right? You can just count that. There's no uncertainty. Define values, 100 centimeters in 1 meter, 60 seconds in a minute, 2.54 centimeters in an inch. Things that you do not have to measure. They're just known equalities, known values, or numbers and formulas. 1/2 base times height, the area of a right triangle. That 1/2, you always use 1/2. You're never going to do a third. You're never going to do a quarter. It's always 1/2 base height. Those are things that are said to be exact numbers. There's no uncertainty, so they are said to have an infinite number of significant digits. Now you can write the word infinite or you can draw the symbol. These are the numbers that, or these, exact numbers do not come up as frequently in this course. They definitely come up occasionally, but they're the ones that are easier to deal with. All right, and just remember, they do not have significant digits associated with them. They are an infinite number because they weren't measured. Now, just remember, if you can count it without the use of any kind of measuring device, it is an exact number. Now, what gets a little more complicated is when measuring is involved, and these are what are referred to as inexact numbers. And really, anytime anyone is measuring something, whether it's using a ruler or a graduated cylinder or triple beam balance or anything like that, there's always a little bit of guesswork involved. There's some judgment, and since you have to use a judgment call, this is where we get into inexact numbers, and this is where significant digits come up. So the picture that's up on the screen, measuring this pencil, I could have 4 or 5 different people measure this and give me 4 very slightly different measurements, and if they're done correctly, I would say they could all actually be correct. All right, so for this one, all right, you see how it's not landing right on the line. You're going to have to do a little bit of guesswork for that. You're not just counting numbers, or it's not part of an equality. Now, key thing here, and it's what's underlined, when you make any kind of measurement, you have to estimate one place past what is actually known. And when I say what is actually known, I'm talking about the calibrations on this ruler here. Each of these little lines is a calibration. All right, so you know here's 8. There's 1 line after it. There's 2 lines, so 8.1, 8.2. It looks like this pencil's a little bit 8 past 8.2. So that 0.2 is the known part, and you would have to guess the number that's going to come after that. So that's what I mean when I say past what is actually known. It's past the smallest calibration on whatever equipment you are using. Now that last digit is always the estimated digit, and that's the part where I said a little bit of guesswork comes into play, and that's why I said I could have 4 or 5 different people measure this pencil and give me 4 or 5 different numbers, slightly different numbers, but they could all be correct, and it's because that last digit is guessed. Now, a lot of times, well, if you were in class, you would be using a graduated cylinder. I think what's going to happen in this virtual world is that you are just going to see pictures or video of graduated cylinders. But you want to read a graduated cylinder the right way. You always get this meniscus, and it has to do with the surface tension of the liquid. And usually for us, it's water or water-based. So you're going to have the liquid kind of move up the sides of the graduated cylinder. You want to read it at the bottom, right? And you want to keep your eye at the level of that meniscus, because if your eye's below it, it's going to give you a false reading, or if you're above it, it's going to give it a false reading. You have to make sure your eye's right at the meniscus. So examples of figuring out significant digits. Whenever you are using any type of measuring equipment, first thing you want to do is figure out what is the resolution, or what do each of these lines mean, the calibration. So when I look at this, it's going from 30 to 40, and there's several lines in between. So each line in this case is counting as 1. 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. So you know that this liquid is between 36 and 37. Now this one's an easy one to remember because it looks like it's right in the middle. Now for me, I actually said 36.4 milliliters, and I did that just to show you, if you're looking at it and you thought it was 36.5, I would not mark that wrong. As long as you have 36 point and then some number guessed here, it's going to end up being okay. You have to remember to include this last digit. The 4 is the estimated digit. So you're estimating one place past what you know. You know the 36, and you guess that next number in line. All right, so now for this one, pay attention to what each of the lines means. It looks like each line means a milliliter again, 16, 17, 18, 19, 20. Now this is one that's easy to forget. People look at this and it lands right on the line, and a lot of people write it down as 19. But you should really do it as 19.0. You know with certainty the 19, and you guess the next number in line. If you just wrote that as 19, if somebody was writing or reading a lab report that you wrote, you would not be representing the accuracy or the precision of the equipment that you used. Right? So you have to include that last estimated digit. When it lands right on the line, it's very easy to forget to do that. All right, now this one's going from 6 to 7. So now each of these lines is not 0.1 anymore. I'm sorry, each line is not 1 milliliter, it's 0.1. So this is 6.1, 6.2, 6.3, and so on. So it's somewhere between 6.2 and 6.3. So you have to take a guess. 6.25. You know with certainty the 6.2, you guess the next number in line, that 5. All right, so for something like this, just another example, figure out what each little line means. Each calibration is 0.1, so you have to estimate to the 0.01 place. You estimate one place past what you know. So for me, I thought it was 8.76. Now, you can have a different number for this last digit, and that's okay. You need 8.7 and an estimated digit. Something like this, again, is really, really easy to mess this up. Again, look at what each line means. It counts as 0.1, so you have to estimate to the 0.01 spot, the hundredth spot. So for me, I thought it was 8.00 because it looks like it lands, that meniscus lands right on that line. We don't use these too often. I don't know why. I just kind of get annoyed by ones that go up by 0.2. So since each one goes up by 0.2, you could still only estimate to the first decimal place, right? The difference was the other ones went up by 0.1 or 1. Now this is 0.2, right? So you could just go to 8.0 for that. If it was somewhere in the middle, you would say 8.1. That's as close as you could get for that. All right, so significant digits. Remember, it's the numbers that you know for certainty plus that estimated digit. There's a bunch of rules for counting significant digits, and I mean, if you want to, you can try to memorize these, although to be honest, I don't think it's worth doing it that way. There's a little trick you can use to remember it. Anything that's a non-zero number is always going to count no matter what. So 132.54 grams, that has 5 significant digits. If zeros are really the only thing that you have to pay attention to when counting significant digits, right? Any non-zero digit's going to count no matter what. The zeros are where it gets a little tricky. Now, if the zeros are sandwiched between non-zero numbers, then they are going to count. So in this case, 130.0054. They all count as significant. That was a meaningful part of that measurement. Now, if they are at the end of the number or at the beginning of the number, the zeros, that's where you really have to pay attention. It all depends on whether a decimal point is there. So 190,000, no decimal point, that only has 2 significant digits. 190,000 with a decimal point has 6, right? So it looks like it's the same number, but really the difference is this decimal point. Right, so what we have to do is pay attention to the decimal point. An easy way to remember it is think of a map of the United States and about where the Pacific Ocean and the Atlantic Ocean are. And this is one of those things where if you go by anybody's classroom at the beginning of the year, any chemistry teacher's classroom, they're probably going to be talking about this. So if a decimal point is present, you start at the Pacific side. And this is why people do this, because the P's match up. Present, Pacific. Atlantic means the decimal point is absent. You're going to start from the right and work your way left. If the decimal point's present, you start from the left and work your way right. So what do I mean with that? And these are the examples at the top of the page. If you're in my packet, this is the very top of page 3. So for these, if I'm asking you to count significant digits, you always look for a decimal point. It's present. So you're going to start from the Pacific side. So you cross out all the zeros. You don't want to just like erase these or something like that. It's just saying that these do not count as significant. Once you get to the first non-zero digit, you start counting everything to the right of that count. So in this case, there's 2 significant digits. Now in this case, those zeros are sandwiched between non-zero numbers. So the first number you get to is a 1. And remember, you start from the left because the decimal point is present. You start from the Pacific side. So everything counts. That's 5 significant digits. Now the next one, those leading zeros are not significant. All right, so when you do this, you just count it up. There's 5 left. Once you get to that 2, everything to the right counts. And now the last one, decimal point's present. You start it on the left-hand side, work your way right. All of those digits count. All right, so now what we're going to look at is if the decimal point is absent. So there's no decimal point here, but notice there's no zeros either. So they're all going to count. All right, these zeros are sandwiched between non-zero numbers, so they're going to count, regardless of whether there's a decimal point or not. All right, now this one, 14,100, no decimal point. So you're going to start from the right, work your way left. Those trailing zeros are not significant. So what happens there is they are just 3 significant digits, and then that 0 is sandwiched, so that is 3 significant digits. All right, so I'm going to stop there for this recording. So we did the SI unit, or the SI International System of Units, the metric system prefixes, what they mean, and counting significant digits.